For decades, software engineers relied on a predictable hardware cycle. A standard single-threaded program would naturally run faster every few years as manufacturers continually increased the clock speed of their central processing units. This chart plots 40 years of microprocessor data. Around 2005, the green frequency and blue single-thread performance lines hit a plateau, reaching their physical limits. Engineers adapted horizontally. The orange transistor line climbed, and the black line emerged, showing multiple cores on one chip. This hardware pivot created a crisis for legacy software. A traditional serial program executes one instruction at a time, meaning it only utilizes one core, while the rest of a multi-core processor sits idle. Capturing the performance potential of modern hardware now requires rebuilding logic for parallel execution. Flynn's taxonomy details how computer architectures manage instructions and data. The bottom left quadrant is traditional serial programming, SISD, or single instruction, single data. Utilizing modern hardware requires migrating logic to the right side of this grid, into the MIMD and SIMD quadrants. Mastering these quadrants requires navigating three distinct computational topologies. First, shared memory, second, distributed memory, and massively parallel graphics processing units. In a shared memory architecture, multiple processing cores live on a single motherboard and read from the same physical block of RAM. Developers use the POSIX thread standard, or pthreads, to spawn concurrent execution pipelines that operate side by side within this shared space. Sharing that space introduces the threat of thread interference. If two threads attempt to modify the same variable at the same millisecond, the data corrupts. We define the lines of code modifying global resources as the critical section. To protect data, developers use a mutex. When thread A reaches the critical section, it locks the mutex, writes its data, and forces thread B to wait until the lock is released. When strict binary locking is too rigid, engineers use semaphores to maintain a count, allowing a specific number of threads to access a pool of resources simultaneously. Explicit synchronization introduces the risk of deadlocks, where threads freeze indefinitely while waiting on locks held by each other. Shared memory is fast because the data never leaves the motherboard, but it requires the developer to manually manage thread states and prevent deadlocks. When datasets exceed the capacity of a single motherboard, processing requires linking thousands of individual computers into a cluster. This is distributed memory computing, which relies on the Message Passing Interface, or MPI standard. In this architecture, memory is strictly isolated. A process running on node A has no visibility into the RAM of node B. To collaborate, the software must manually package data and transmit it over a network channel to the receiving node. MPI enables scaling across thousands of nodes in a cluster, but it trades raw processing speed for the time required to move data over a network. The hybrid model divides a large dataset into chunks at the top of the diagram. MPI handles the macro-level distribution of these chunks to separate physical nodes. Once a node receives its chunk, OpenMP threads take over the micro-level execution, fully utilizing the local CPU. This model optimizes performance by minimizing network transfers while maximizing localized memory access. Uniform workloads like image processing involve performing the same mathematical operation millions of times. These map to the SIMD quadrant and a different hardware topography. While a standard CPU contains a few complex arithmetic logic units, a graphics processing unit packs in thousands of tiny, simple ALUs. Cuda is the framework that allows CTOAD to execute on these thousands of processors for general-purpose GPU computing. Cuda separates memory into the host, the CPU RAM, and the device, the GPU's onboard video RAM. Developers must manually allocate space on the device and explicitly copy data across the system bus from the host to the GPU. The CPU then launches the kernel, a function dispatched across a hierarchy of grids and blocks that wakes up thousands of GPU threads simultaneously. Because every thread runs the same function, developers use coordinate formulas to route each individual thread to a different index in the dataset. Once the math is complete, the results are copied back across the bus from the device to the host. Cuda sacrifices general-purpose flexibility for high-volume mathematical throughput, provided the developer maintains strict control over the host-to-device data pipelines. High-performance engineering relies on matching the algorithm's concurrency model to the physical layout of the hardware. For tightly coupled tasks on a single machine, we deploy the shared memory models of POSIX threads and OpenMP. For workloads that scale across large-scale clusters, we deploy MPI to manage distributed memory. For mathematically dense tasks, Cuda orchestrates the thousands of simultaneous operations the GPU is built for. Modern software performance is the art of matching an algorithm's concurrency model to the physical topography of the hardware.